Okay, in today's lesson, we're going to be learning about piecewise defined functions and also absolute value functions. So a piecewise function is exactly what it sounds like. It's where you graph pieces of functions over non-overlapping intervals to make it still a function. So for example, right here, if we have f of x is equal to x squared minus 3, where x is less than or equal to 0, and 1/4 x plus 1 when x is greater than 0, what's going to happen is we're going to graph a piece of this parabola and then a piece of this line. So what I've done is just written the two graphs over to the right, but we're only going to graph it for the intervals that it gives us. You can see in here, if we look in Desmos, we've graphed a piece of the parabola, x squared minus 3, but we've only graphed it for when x is less than or equal to 0. And then we've graphed a piece of this line for when x is greater than 0. Unfortunately, because I'm using Desmos, you cannot see the open and closed holes, but when we get to graphing, we will show you those. Okay, so for this next one, it's got two lines. It's got y equals negative 2x minus 2 and y equals x plus 3. To help you get started, just substitute some input values, some domain values in, and figure out your range values. So for example, if we substitute in negative 4, we would substitute it into the top function because that is the function that we're using when x is less than negative 1. So when we substitute negative 4 in, we would get 6. When we substitute negative 3 in, negative 2 times negative 3 minus 2, we would get 4. And when we substitute negative 2 in, we would get 2. However, when we get to the x value of negative 1, we have to switch to the second function because this is the function we're using whenever x is greater than or equal to negative 1. So we now start substituting into x plus 3. So negative 1 plus 3 is 2. And then this would give us 3, 4, and 5. All right, for some students, it's really helpful when they first start graphing piecewise functions to just graph the entire function and then erase the part they don't need. So what I mean by that is, let's say I go and I graph the graph y equals negative 2x minus 2. The y-intercept would be at negative 2. The slope is negative 2, so we would go down 2, right 1, down 2, right 1, or in the opposite direction, up 2, back 1, up 2, back 1. And then we would graph our line. However, we know that we really only want to graph the line for when x is less than negative 1. So instead of me graphing the entire line, I'm only going to graph that part. Then I'm going to use my eraser and go back and erase the rest of it. Also, it says less than, not equal to. So what we want to do to show that we want to graph all values up to negative 1, but not including negative 1, is where x is equal to negative 1, which is this value right here. I put an open hole. It's much easier to use a pencil than this tablet. So that shows that we're graphing this line for all values less than negative 1, but not including negative 1. And then we'll do the same thing for the other graph. So this y-intercept is at positive 3. And the slope is 1, so we're going up 1, right 1. But if we went down 1, back 1, we could get this line. Now, you could graph the whole thing, but we really only want to graph it for when x is greater than or equal to negative 1. So we're going to only graph this side of it. Something else sometimes some of my students like to do is wherever that interval changes, where in this case it's where x is equal to negative 1, they'll go and put a really light dashed line where x equals negative 1. So they know that that is where the switch is. Okay, I'm going to graph this function up to that line and then the other function from that line. And that may help you. And you can see what we're doing is graphing pieces of functions. It also asks us to state our domain and our range. Well, if you look at it, guys, as we look from left to right, we have graphed every x value. Even though there's an open hole on the first graph, there's a closed hole right above it, so it's still covering that x value. So the domain of this function would be all real numbers. And remember, using interval notation, we write that from negative infinity to infinity. The range of this function, however, is not all real numbers because the lowest value graphed on here is 0, but it actually never gets to 0. So what we would do for the range is we would say from 0 to infinity, not including 0. All right, why don't you pause the video and try the next one. So in this case, we have two constant functions and then that quadratic function. So I've gone ahead and put those dashed lines at negative 1 and positive 1 because that's where the intervals switch. So we want to graph y equals -2 for when x is less than -1. So for that graph, it's just a constant function at -2. So we're going to just graph this horizontal line. But when we get to -1, we're going to put an open hole because we do not want to include that value because it's not equal to right here. Then we're just going to graph our basic parabola from -1 to +1. So we know that that goes through the origin at 0, 0. And when we go out 1, we go up 1. But when we go out 1 over here, it would be an open hole when we go up 1 because it includes -1 in the domain for this function, but not +1. Then, for the last part, we're going to graph for when x is greater than or equal to 1, we're going to graph y equals 1, which is another constant function. However, because it includes 1 here and it actually ends up closing in that open hole and looking like this. Now, of course, I'm just trying to use the different colors so that you can see the different pieces of the function, but you can just use a pencil. All right, so what is the domain of this function? Well, the domain, again, is all real numbers because it actually covers every x value on the graph. The range, however, that one's a little bit weird because the range is just at -2. So it's like -2 by itself. So if you're using an old notation, you could say -2 to -2, even though that doesn't really go anywhere. Or you could just use a little bracket, like squiggly bracket, just -2. And then in union with, and then it goes from 0 up to 1. So, and it includes both of those values, so 0 to 1. Remember, your domain is your x values, your range is your y values. Now we're going to use that h of x function to evaluate the function at the following values. So it says, what is h of -3? So in this case, we would substitute into the very top function, and the answer would just be -2 because it's a constant function. What is h of 0? Because 0 is between -1 and 1, we would substitute in the middle function, which is x squared, and 0 squared is just 0. And then for h of 2, because 2 is greater than or equal to 1, we would substitute into the bottom function, which is just 1 because it's a constant function. So then it asks us to add those values together. So if we add those values, -2 plus 0 plus 1 would ultimately give us -1. Okay, so try the next one. Pause the video, and when you're done, start the video back. Okay, so for -2, we would substitute into the very first function. We get -6. For 0, we would substitute into the middle function, because you have to substitute within the interval where that domain value falls. But in this case, because that is 1 divided by 0, we know that is undefined. And then the last one, we would substitute for 2 into x cubed, and we get 8. Which input is not in the domain, and why not? 0. And it's because we cannot divide by 0, therefore the domain value of 0 is undefined. All right, let's look at this next one. This is another piecewise function. I would like for y'all to try it on your own, make the table, graph it, state the domain and range, and then start the video back. Okay, so this is also 2 pieces of lines, and when you put it together, it ends up being a V shape. So in this case, guys, this is actually the definition of an absolute value. An absolute value function can be written as a piecewise function because what happens is anytime you substitute a negative value into your absolute bars, it makes it positive. Where anytime you substitute 0 or a positive value, it just stays the same. So that's why if you look over here, that's how the absolute value function is defined. And that's what we're going to be working with for the rest of this lesson is working with the absolute value function and transformations of the absolute value function. And this is one of those things we call a parent graph. Just like when you learned y equals x squared back in Math 2 and you had to know it inside out, this is going to be the same. Now, I'm not saying you can't use technology to check yourself or try to discover things, but you should know this graph and you should be able to transform it without the use of Desmos or your graphing calculator. So keep that in mind. All right, so shifts and stretches. What happens when we perform operations to these functions? You should have talked about this back in Math 2. A good thing to do if you really don't understand your transformations is to play with Desmos, and I'm going to show you real quick how to do that using the absolute value function. All right, so when you go into Desmos, just click y equals, pull up your little tablet, and you can type in absolute value by clicking this right here. And so we could put x, and then we can arrow out, And instead of putting a number there, just put like plus C. And what it will do is it'll allow you to add a slider. And so then you can see the effect of adding or subtracting, because if it's negative, it'd be like subtracting a value to the outside. So when C is 0, you can see you just have your parent function. So as we increase it, you can see it moves up. As we decrease it, you can see it moves down. Then you could do the same thing, come in here, but change it to minus C inside. And you can see the effect when C is, I'm going to go back to being 0 real quick. So there's your parent function. So if C is a positive number, it actually moves it to the right. So like if you have the absolute value of x minus 2, it doesn't go left 2, it goes right 2, and vice versa. So I just suggest play with it, put the C's in different places, and kind of go through and rediscover these different transformations and the effect of them. Okay, so here are the different transformations that happen when we perform operations to any function. And even though we're going to focus on an absolute value function right now, it doesn't matter what the function is, and you'll see that as we go through the semester. The actual transformation is the same: shrinking, stretching, moving up, left, right, down. So go ahead and get these down, and then we will expand upon this in class. You might want to pause the video so you can write it down and then restart. All right, so for these, the directions are actually backwards. What I would do is I would describe the transformation first, then graph it, then state the domain and range. So go ahead, pause the video, see if you can figure out what would the transformation be, and then restart. So for that first one, it's going to reflect over the x-axis, and it's going to move up 4. The second one is just going to move down 2. So remember, you've got to learn that absolute value function, that V-shaped graph, and that's what we're going to be doing. So we're actually going to, if you think about it, it's like instead of it opening upward, it's going to open downward. So you're just going to flip it over, and then it's going to shift up 4 units. So instead of the vertex being at 0, 0, the vertex is now going to be at 0, 4. But instead of it opening up, it's going to open down. And we didn't shrink or stretch it any, so it's just kind of like those slopes of -1 and +1 on each side, but it's opening downward. And there's our graph. So what's our domain? Our domain is all real numbers. Absolute value functions, the domain is always real numbers unless you restrict the domain for some reason in like a piecewise function situation or a real scenario situation. And then the range in this case is going to be from -infinity, because it goes down forever, all the way up to 4, including 4. So we would say -infinity to 4 with a bracket. All right, so looking at the second one, the only thing that happened in this case is it shifted down 2. So we're just going to take that parent absolute value function, that V-shaped function, and we're going to shift it down 2. So instead of it being the vertex being at 0, 0, it's going to be at 0, -2. And then we just graph our parent graph. It's like you just pretend that you're at the origin once you get that shift in there. Okay, and the domain in this case is still going to be all real numbers. But the range in this case is going to be from -2 to infinity, because this one opens up. All right, try the next 2 completely on your own, and then start the video back and see if you get it right. Okay, so the first graph stretches vertically by a factor of 3, so it's 3 times the range. And the second one goes left 5, so it's just like we pick up that parent function and we shift it left 5 units. So the vertex is at -5, 0. Again, guys, you should be able to do this without a calculator. So push yourself. Try to do these graphs without using Desmos or your graphing calculator. But there's nothing wrong with then checking with Desmos or your graphing calculator. You are still in the process of learning this, but push yourself to do it without the technology and then check yourself. I do think Desmos is a great resource. I love looking here at this graph. What I've done is I've graphed the parent function, and then I've graphed that y equals 3 times the absolute value of x. And you can see it's like it pulled that parent function and it stretched it vertically by a factor of 3. If you check any point on here, like here's the point 1, 1 right there. If you look at it on the other graph, you have the point 1, 3 on there. Every y value is now 3 times what it was. Okay, so try the next 4 graphs, see how you do, and then we will discuss them later in class together. Good luck.